Welcome back to another about to rain day in Thailand. We are definitely in rainy season, even though it's European summer holidays right now, and I've seen a lot more people walking around town just in time for some rain. Now, as you saw in the previous video, we now have the version 2 board fully soldered up. Here's version 1 for inspiration. Version 2 plugged into the ICE. ICE is plugged into the laptop. Let's power the board up. And you can see we have the green light and the red light, which means they are communicating to some extent. Let's pop over to Atmel Studio and see if we can actually talk with the board. Okay, I loaded up my code exactly as it was running in the version 1 board. And to get the ICE talking to version 2 board, we click here for device programming. We say we're on Atmel ICE. We're talking to this chip through the single wire debug interface. If I click apply, now we've got the serial number of the Atmel ICE. So that means the laptop and Atmel Studio are talking to the ICE board, which is good. Now here's where we find out if the chip is actually running. If I click read, we get back the device signature. Hex 110103A is the signature from Atmel for the ATSAM C21E18 chip. So we are live talking with the board and the chip are running at 5 volts. So we are up and running with the version 2 board. Now let's see what we can see from the code. All right, so let's say start debugging and break on the first line of code. So if I click here, it builds all my code and we jump into the debugger, and we are now sitting just before the first line of the main function, which is the main entry point. If I click on step over, every time I click, I'm executing that line of code, and I can see the little green light on the in-circuit emulator flash every time I click on a line. So we are now running code on the board, which is great. Now, I don't have a current source or voltage source hooked up to the board, but I'm assuming all that works from before. So I'm going to work on adding some of the newer features for version 2. First, I'm going to add the blinking light, which I'm going to use as a visual indicator of the health of the board. If it's nicely flashing, that means everything's good. Otherwise, I can flash an error code, which will really help me to just look at the board when it's in the bike. Without hooking a laptop up to it, I'll be able to decode any potential problems. And Blinky is alive. Took me a while to work it all out, but let's pop over and I'll show you what's what in the software. Okay, the first thing I had to do in order to make the LED blink was to create a timer. And I want to set that timer up so that it fires an interrupt into my code every now and then I can change the state of the LED. So I created a timer, which is connected to the real-time clock inside the chip. Then we configure the timer. It was very straightforward. I don't provide an external oscillator in the circuit, so I'm depending on the one that the chip derives internally, which is 32.77 kilohertz, which is fine. Then there's a couple more things down here that you can do. This Prescaler lets you divide by a certain number before the clock fires into your software, and I'm just going to leave that as 1. And then this compare value, I set it to 32.77 because I basically want this to fire every, make the basic clock tick in my software to be 1/1000th of a second or 1 millisecond. So I'm thinking if I set this to 32.77, divide that into 32,777, that gives me 1,000. Then we come over into my source code. and I initialize the timer to be what I think is 500 ticks, which is 500 milliseconds, which is half a second. After this period of time passes, I want it to call my Blinky LED callback function and do it in a repeating fashion. So I add this timer task to timer 0, and I start timer 0. Then what happens is when 500 milliseconds are finished, it calls into my Blinky LED callback function. Now, I'm thinking ahead to error codes, but I'm just ignoring that for now. So my error code is 0, and I will come straight down here and toggle the pin connected to my LED, and this will make it go from on to off to on to off, and that's exactly what we're seeing with the Blinky LED on the board. Now I set up a timer with my phone, and it's not giving me exactly 500 milliseconds of delay. I don't know if that has to do with this function here, this compare value, but it's close enough for flashing an LED, so I'm okay with that. Welcome back to another sunny and cool day in Thailand. Today is actually New Year's Eve, and it's almost sunset. We are back to the DC current and voltage CANBus board version 2. I apologize for the massive delay, but I got sidetracked by squirrel. I was working on the lithium battery pack down here and over here and all the other stuff going on. I just got distracted a lot, but now I need to come back here because I have the factory lithium battery in the bike right now, and it's driving around nicely. So we're going to jump into this full steam and get going in the code. Now, just to pick up with what we left off last time, we're adding in the functionality for the USB chip, which is right there. Now, when I first plugged the chip in and enabled it in the software, which I'll describe in a minute, the chip got scorching hot, and I think it's because I did a bad soldering job. But if you look at this thing under some light, it is small, and difficult to solder because all the pins are underneath. There are no pins externally like the main CPU. So I've actually started watching this guy called Louis Rossmann on YouTube who fixes Apple products at his store in Manhattan, and I picked up a lot of great soldering tips from him. So I've put a new USB chip in there using my hot air soldering station, and when I power the thing on, it doesn't get hot anymore. Now, it doesn't do anything because the software is not set up, but at least it's not melting down. So let's go ahead and jump into the software. Okay, to make the USB bus work, we have to add this factor in our software setup. It is a USART, or Universal Synchronous Asynchronous Receiver Transmitter, otherwise known as a serial port with a whole bunch of steroids attached to it. And of course, you can connect one of these into your software configuration within Atmel Start, and then, as with the other components, you get to define its functionality. So we are using the USART synchronous driver. We're putting in UART mode, and we're using the SIRCOM0 instance, which is one of 4 that we can choose. If I pop back into the schematic software here, you'll see that I've defined it on the SIRCOM0 instance, and the transmit pin is PA08 and the receive is PA09. So if we go back, transmit PA08, receive PA09, and we're not messing around with anything else there. We're turning buffering on because buffers are good. No parity, 8-bit, 1-stop bit, 9600 baud, because that's the most common way that you connect to a serial port. So let's go ahead and add this to our configuration and then start writing some software to drive the USB bus. In order to write to the USB port for whatever message we want to send out, I've written a little routine called USB write. I have to pass in a pointer to the data I want to write and its length. Because C is dumb, it doesn't understand objects which are strings, so you always have to pass it some point in memory and the length. And if we go down to our Blinky routine, you can see I set up a string called hello USB exclamation point. I then calculate the length of that string, and I call my USB write function with the start of the string and the length. And if we come down to my little routine right here, I retrieve that, the pointer to the string and the length, and I use some Atmel magic to set up the serial port descriptor. I enable synchronous writing, and I write to the I/O port defined for USART 0, the string and the length. And that should get us our string of the serial port. Now, there's no carriage return line feed, so this is all just going to be mashed up on the same line. But that's good for a first try. Well, it looks like third time's a charm for soldering the USB chip. Windows thinks we actually have a USB to UART bridge registered on COM16. Let's see if we can talk to it. The first two times, well, the first time it got really hot. The second time it just wouldn't talk. It detected something on COM16. Let's connect to it. Ah, yes. Hello, USB. That's coming from our firmware. Every half a second, we get another one. That's awesome. Okay. I had to go to this external serial port monitor because I had a hard time finding it inside the Atmel tool. Let's go and see if we can find it now. In order to see what's coming across a serial port, you have to go through kind of a convoluted path. You go to Data Visualizer, and right now the system is getting data through the Atmel ICE box, and that's fine. But we want to set up an external connection to a serial port. 9600, no parity, one stop bit, open the terminal. Now this is weirdly blank, but it's kind of this blue color. I'm going to hit connect, and there we have it. So I can minimize that thing, and now I see our hello USB data coming through inside the tool. So now we can progress with the values we want to be displaying. Okay, I think I'm going to wrap it up here. It's almost 7 o'clock on New Year's Eve. I'm going to get cleaned up and go down to the beach and find some of my buddies and get some drinks with little umbrellas in them and welcome in the new year with some fireworks. But the fireworks we have here is green blinking light. Sorry, bad joke. Okay, just wanted to give you an update that I'm jumping back on this project, and I should have some more progress in the next few weeks. Thanks. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.